So we're in the 5th lecture on entropy as a property and using it to quantify the second law of thermodynamics. We talked about closed and open systems. We talked about isentropic processes. An isentropic process has what property that's constant? Entropy. S is equal to a constant. Now we need to talk about first law analysis for open system describing a steam turbine and basically a gas turbine. Talk about turbines. And when we talk about turbines, they're devices that have a purpose. We want them to do something. Hence, we have a measure of their efficiency, how well they work. And then we'll talk about gas compressors as well. So let's jump into it and take a look at a problem. So steam enters a well-insulated turbine. Maybe you put the turbine like this, and it's well insulated. So what is Q? 0. And the rest of the problem, you read it, it enters at state 1 and the pressure and temperature are given, and it exits at state 2 and the pressure is given, and the purpose is to produce some work per unit mass of the steam that goes through. So we would calculate the maximum possible work produced in the turbine in units of kilojoules per kilogram. All right. Well, let's list all the information given. Property 1 is 8 megapascal. Temperature 1 is 400 degrees C. We could list other properties, but the properties of interest are going to be H1 and S1. And then think about state 2. We're going to have the pressure at 2, the temperature at 2, the enthalpy at 2, the entropy at 2. That's a pretty good start on our list of properties. All right. So if you do a first law analysis around this turbine, first law really is a statement of the conservation of energy, and it's an energy balance. And you have negligible heat transfer. You have no change in kinetic energy of the flow, no change in potential energy. There's no information given. You just assume. If it's not given, we're going to assume it's negligible. And you've done a first law analysis before, and what you find is that the work developed by the turbine is the difference in the enthalpy of the flowing fluid. It comes in high energy content, high enthalpy. It goes out low energy content, lower H2. Hence, the steam, the energy in the steam, some of it was converted into shaft power, shaft work. How much of it? The difference between the enthalpies. So then you say, well, I have to go and I have to do the second law. And maybe the second law of thermodynamics, an entropy balance for that system, for the same control volume, gives you something like this with a little bit of work. It gives you that the exit entropy is equal to the inlet entropy plus the sigma dot per m dot. There's no heat transfer. There's no entropy transfer with the heat. It's operating steady state. And you manipulate it, and there you go. Does that equation look reasonable? And I write it like that so I can read it. It says the inlet entropy plus how much is generated because of irreversibilities has to be taken out of the system. The exit entropy has to be larger than the inlet. By how much? Sigma dot over m dot. All right. Now, this key word, maximum possible work, is a little clue. What do you think this term should be? Sigma dot over m dot. Should it be large negative equal to 0 or large positive? Okay, let's do a clicker question. Should it be A, much less than 0? I can't even spell. How about this one? Just say sigma dot over m dot. Should it be much, much less than 0, sigma dot over m dot. Should it be equal to 0 or sigma dot over m dot much, much greater than 0? Answer A, B, or C. And I know you would like to have more time to answer these questions. Is 24 seconds enough? Which one would you really like so that you can get the maximum? I'm going to give you a little more time. There. You want the maximum possible work produced. This is much, much less, and this is much, much greater. All right, down to 3 seconds. All right, we're in. Okay, now, what about sigma dot divided by m dot being less than 0? Can it be negative? That violates the second law of thermodynamics. A lot of times people come up with schemes to get more work out of a turbine from some clever design, and energy balance, that looks okay. Energy balance looks okay. You look at the second law, you say, sorry, it's not going to work. It violates the second law of thermodynamics. So this is not a good answer. All right. This is the best answer. What is friction and irreversibility? If you have a lot of friction in there, do you think you're going to be able to produce a lot of power? Intuitively, friction's bad for energy conversion going from heat into work. The energy content due to pressure, temperature, the steam, convert that as best you can into work. That's hard. Friction's not going to help. So the best answer is B. Now, let me spend a little time on this. This is a temperature entropy diagram. Can you see that? A TS diagram. It's drawn to scale. It's plotted with ref prop. It's real steam data properties. What's the big red bold line for? The dome. What's at the top of the dome? Critical point. All right. So it says that the steam comes in at 8 megapascal and 400 degrees C. Where is that on this TS diagram? Well, 400 degrees C, and here's a line of 7 megapascal and 20 megapascal. So you have to do a little interpolation in between visibly. Maybe right there is 8 megapascal. That's the inlet state coming in. Can you describe the steam coming in? Is it subcooled liquid, two-phase, superheated? Superheated vapor. Yeah, superheated vapor. Now, some people may say it's above the critical point, so it may be, well, whatever. You could call it slightly, supercritical something, but it's superheated vapor is good. Now, if I pass it through the steam turbine and I'm interested in the outlet property, I know the outlet pressure right here is 0.1 megapascal. Let's take a look at the line of 0.1 megapascal. It's right here. Somewhere along this line is state 2. Can you see that? It has to be, because that's the outlet pressure. Can't be anywhere else but along that line. Now you ask, okay, if this is true, that sigma dot's equal to 0, somebody suspects that's the best performance to get the most out, where is state 2? It's not by knowing pressure and temperature. No. Not by knowing pressure and enthalpy. No. It's by knowing pressure and entropy. Because the second law says if sigma dot over m dot is truly equal to 0, what is the difference between... what did I write? How come people are staring at me? This is terrible. How long did I have that typo up there? Look it. If I was a student and they had errors like that, my head would be spinning. It'd be like, what do I trust? What do I not trust? What's correct? What's incorrect? Yeah, I'm going to fail. The instructor messed me up. He put sigma when he should have put S. That's it. The whole lecture's a waste. How many people were sitting there waiting for me to find that error? Do me a favor and catch my error a little earlier for me, please. I mean, you'll do me a favor because I'm embarrassed now. Can you see me turning red? All right. Now, sorry about that. So S2 is equal to S1 when sigma dot over m dot is equal to 0. So where is state 2? Straight below, and you come straight down, and there is state 2. Describe state 2 to me. Two-phase liquid vapor mixture with a pretty hefty quality. It's a pretty high quality, okay? So way I find H2, because the goal is to find this maximum power, energy per unit mass, that maximum work out of the turbine, I need to get H2. Well, it's a two-step process. X2 is intermediate. Oh, I forgot the name of X. What is that property, X? Quality at state 2. I'm going to calculate it from S2 minus S of F divided by Sg minus S of F. I'm going to get the quality at state 2, and then I'm going to come up here to get H2, H of F plus the quality at 2, H of Fg. Property evaluations. You've mastered that, hopefully. Okay. So now that I get to H2, then I can calculate the maximum work. Somebody says, well, maybe a little bit of entropy generation would be good. How do you really know, Professor? Well, do me a favor here. Let's say if I do have a small amount of sigma dot over m dot, some irreversibilities. Tell me the difference. What's the change in S2? Does S2 go down or does it go up compared to S1? It goes up. So S2 may sneak over a little bit like right here. Let me try and draw it here, or here, or here, or here, or here, or here. True? But let's consider the case where there's just a little bit of entropy production. Can you tell if it's really right here? What does the quality do? What did X2 do? Did the quality at state 2 go up a little bit? Or go down a little bit? It went up a little bit. How about if it went all the way to this point, enough entropy was generated, what comes out right here? If that would have been the outlet. Saturated vapor. What's the quality of saturated vapor? 100%. Let's say it even more and more. Well, it's now coming out superheated vapor. Can you see that the enthalpy, the exit enthalpy is going up, 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 up. H2 is going up, 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 up as sigma dot over m dot increases. If I have more irreversibilities, the exit enthalpy goes up just like the exit entropy goes up. Okay? All right. Just do this one. Let's say the first case, if you want to put some numbers in, this is 0.8356. And my exit enthalpy, H2, is 2304.2. The inlet enthalpy is 3138.3. And the maximum work out of the turbine comes in at 834 kilojoules per kilogram. Again, if you say, well, let's let this change from 83 to 93%, what do you think this is going to do? It's going to go up. Hence, if that goes up, you want it H1 to be a lot larger than H2, but the difference is getting smaller, you get less work out. So the maximum possible work produced by a well-insulated steam turbine, neglecting changes in kinetic and potential energy, is sigma dot over m dot equal to 0. It's isentropic expansion of the steam. Isentropic expansion in the steam. All right. Somebody says well-insulated Steam turbine at 8 megapascal, 400 degrees C. It's going to be right around here for the inlet state 1. It exits at 0.1 megapascal. Yep, that's that same problem, 0.1 megapascal. Oh, but it's exiting at 120 degrees C. Where is 120 degrees C? A little bit above 100 degrees C. It's right around here. That's where it actually physically exits. Slightly superheated steam. Because TSAT at the 0.1 megapascal is 100 degrees C, right? Right at 100 degrees C. So if it comes out 120, it's slightly superheated. Now determine the work produced by the turbine. Well, you have the same equation. The work produced by the turbine is H1 minus H2. That didn't change. Make a list of all our temperature 1, pressure 1, enthalpy 1, entropy 1. Then come over here, pressure 2, temperature 2, enthalpy 2, entropy 2. There's no need for quality of 2. There's no quality of 2 for this case. It's coming out superheated, true? So because they gave us the pressure and the temperature on both inlet and outlet, there really isn't much to do. We can just go and make a calculation. We just need, that number didn't change, 3138.3 kilojoules per kilogram. And this number comes just going from pressure 2 and temperature 2, it's slightly superheated. It's 2716.6 kilojoules per kilogram. Hence, the work that the turbine produces is 422 kilojoules per kilogram or thereabouts. What was it before if it was isentropic expansion? When it came down here, the work produced was 834. Now it's only 422. It's not as good. Engineers can measure the performance, or they give metrics for the performance. They report an efficiency of that turbine. What type of efficiency? Well, what's the benchmark that you're comparing against? It's the isentropic efficiency. If you would have expanded isentropically, how much work would you have gotten out? Well, the work turbine, if it would have been isentropic expansion, we calculated to be 834 kilojoules per kilogram. This is the actual. I think we need to go to the drawing board and help improve the design of the steam turbine. And there's a lot of mechanical engineers working out improving designs of equipment like this. Okay? So, what would be the isentropic efficiency of the turbine? The efficiency of the turbine would be defined as what you wanted to get out. You wanted to get it as high as possible, but this is what you actually were able to get compared to the maximum possible out. And so it's 422 divided by 834, and the isentropic efficiency is equal to 51%. Why do they have the word isentropic in there? Because it tells you that's the benchmark. That's the best. It's assuming isentropic expansion through the steam turbine.
It's assuming reversibility.
That's assuming no irreversibilities, which means it's reversible expansion. That's right. Of the steam. So if you want to show it on a diagram, you put a dashed line between 1 and 2. What does the dashed line indicate? There's some irreversibilities occurring during that process from 1 to 2.
So is work always max when it's an isentropic process?
Yes and no, and now we're going to talk about another device. Whoops, I'm going to have to come back to it. We're going to talk about a gas turbine, and then we're going to talk about a gas compressor. All right. And we'll hold that thought. So instead of having steam expanding, we'll have a gas expand. Well, we want to treat that gas as an ideal gas, And in our approximations, I know that sometimes we burn stuff and you put some carbon dioxide and some water vapor mixed with the nitrogen and whatever leftover oxygen and maybe some unburned hydrocarbon. Oh, that's all too complicated. We'll just treat it as pure air. And that's a common assumption in this class, that we may have combustion in a, let's say, a jet engine or a gas turbine, but what we'll do is we'll just model it as air, as an ideal gas. So air enters a well-insulated turbine where it's expanding. It enters at 2 megapascal and 800 Kelvin. It expands to a pressure of 0.1 megapascal. Determine the maximum possible work produced by the turbine. It's the same thing. I have a turbine. I have inlet fluid stream state 1, outlet fluid stream state 2. The goal is to produce as much work as possible. It's well insulated, so what's lowercase q? There's no information about changes in kinetic and changes in potential energy, so it's assumed to be 0. We go ahead and write the first law. Wherever you want to write it, I'll write it down here. The first law, you would have that the work produced by the turbine, even though it's not a steam turbine, it's a gas turbine, you get the same equation. It's H1 minus H2. You write the second law, same equation, same type of behavior. The exit entropy is equal to the inlet entropy plus how much is produced due to irreversibilities, entropy production due to irreversibilities. So if I want to find H2, what you typically do is you think about pressure 1, temperature 1, enthalpy 1, entropy 1, etc. But this is all for an ideal gas. Air behaving as an ideal gas. When you have an ideal gas, a couple equations come to mind. What are some of these equations for an ideal gas? PV is equal to RT. Sometimes or all the time? All the time. During an isothermal process? Yes. During a constant pressure process? Yes. During an isentropic process? Yes. All the time. If air is always behaving as an ideal gas, P times V is equal to RT at all times, at every state. All right. And then the next one is U is a function of temperature only, H is a function of temperature only, and if I'm really interested in getting S, it's a function of temperature and pressure, but often what we do is we're interested in calculating changes in S, and so the equation that you might remember is either C sub P natural log of T2 over T1 minus R natural log of P2 over P1, something like that. True? All right, so now it's not such an easy thing to say what's S1. I can do this. I can say the change in S is equal to S naught at T2 minus S naught at T1 minus R natural log of P2 over P1. I might be able to say what's S naught at 1, but we really only have an equation, either variable specific heats or constant specific heats, for calculating entropy changes of an ideal gas. It's a little different than what we had for steam. All right. So I come in here and I say the pressure is 2 megapascal, the temperature is 800 Kelvin, and I can get the enthalpy from the air tables. What table is that? Table A 20 something? Yeah, table A 22 or 23, I forget the number. It's 821.95 kilojoules per kilogram. I can get also S1 naught, which is 2.71787 kilojoules per kilogram Kelvin. That is not the total entropy. Entropy of an ideal gas function of temperature and pressure. That's just the temperature only part of it. We come over here to the P2. What's the exit pressure? 0.1 megapascal. Do they tell us T2? No. Do they tell us H2? Wish I knew it, then I could get you the maximum work out. That's the goal. I need that H2 right there to get this maximum possible work produced by the turbine. Well, maybe S2 naught is equal to S1 naught. Hey, that may be true. Answer A, that's correct, or answer B, that's not correct. Yes, I like it. No, don't do it. Don't do it. So somebody says, is S2 naught equal to S1 naught? Yes, it is, or no, it's not. I need to give you a little more time. There you go, 1 minute. All right, what I'm going to do is I'm going to go back to something I just said, emphasize it, really emphasize it, talk a little bit about it, and then we'll grade this. But for an ideal gas, this equation is true, 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 true. PV is equal to RT. Enthalpy is a function of temperature only. True, 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 true. This equation right here, I'd like to just talk to a minute. That equation right there. What's that say? It says that a change in S is equal to S naught T2 minus S naught T1 minus R natural log of P2 over P1. All right. So if I come here back to the second law for this problem, and I'm trying to find the maximum possible work produced, I think it's just like a steam turbine. I think I'll get the maximum when sigma dot's equal to 0. True? Got it. Good. So in that case, then, S2 minus S1 is equal to 0. It's isentropic expansion. Is that the same as saying, if I now want to, I'm running out of room, I need to scoot down just a little bit. If I take this equation, I have S2 minus S1 is equal to 0, but how do I calculate the change in entropy? Oh, it's S naught at T2 minus S naught at T1 minus R natural log of P2 over P1. So what's equal to 0? It's everything on the right-hand side. Let me ask this question. Is P2 equal to P1? It is not. P2 is not equal to P1. Here it is, 2 megapascal, 0.1 megapascal. It's high pressure to low pressure. Go through a steam turbine, go through a gas turbine, high pressure to low pressure. Let me ask you this. Is the natural log of P2 over P1 equal to 0? It's not equal to 0. Thank you for answering those, but I have a clicker question now. Is S2 naught equal to S1 naught? Answer A for yes, B for no. And this time I'll only give you 30 seconds. Polling has stopped. Can I rewrite this equation right here? Could I rewrite that equation as S naught at T2 is equal to S naught at T1 plus R natural log of P2 over P1? Could I rewrite that equation like that? Yes, we could? Still got 3 students who think that S naught at T2 is equal to S naught at T1, but it's not. It's equal to S naught at T1 plus R natural log of P2 over P1. That's correct, isn't it? So 95% of the class was correct. What do you think the percent was on the first time I asked the question? You're improving. Things are looking up. Things are looking up, true? So how do I find, it's a multi-step process here. Let me help you a little bit. But what you do is you say, no, 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 I just can't willy-nilly do that. What I have to do is I have to come down to this equation, and I have to put in the 2.71787 plus R 8.314 divided by 28.97 for air, divided by or multiplied by the natural log of the final pressure, 0.1 megapascal, over the inlet pressure, 2 megapascal, and then I find that this S, the 2 naught, is equal to 1.85814. I look in the air tables for where that occurs, and I do a little interpolation, and I find that H is equal to 350.87, and T is equal to 350.4. If I interpolate twice, I get the T as well as the H, but all I really needed was the H. And so the work of the turbine, assuming isentropic expansion, let me write it up here, is equal to 471 kilojoules per kilogram of the air. Make sense? All right, let me do this. I want to go back, and I have this illustration taking up a large part of the screen I haven't talked about yet, have I? What is this diagram? A temperature entropy diagram. And where's my dome? There's no dome for air. Air behaves as an ideal gas. The dome is so far off, it's not even shown. It's way down in the corner off the chart. So we're going to find the state where it's 800 Kelvin and 2 megapascal. There is the initial state 1. What are the blue lines? Lines of constant pressure. All right. Then we're going to expand down to a low pressure. The pressure is 0.1 megapascal. It's this line right here. True? We talked about the maximum work would be isentropic expansion, constant S, down to the final state 2 from initial state 1. If it was not isentropic, but you had some irreversibilities, where would state 2 go? It would stay on the red line at 0.1 megapascal. Would it skip off a little bit going in this direction? It would. It would, right? What would the exit temperature do? It would march up a little bit. Hence, it has more enthalpy going out. That was we wanted to convert. We wanted a large H1 minus H2. We wanted a low H2. We wanted a low T2 to get the maximum work out. So any irreversibilities is bad for performance. Yes, sir?
Just to clarify, to get T2 and H2, you did interpolation.
That's right. You want the details?
No.
It almost landed spot on. It's like a 3.7% of the way between the value at 350 and the value at 360. So you could have almost ignored that interpolation and picked the value of 350, but I did the details. Mm-hmm. All right, so guess what you do next? You talk about the isentropic efficiency. So what you do is you say, okay, we know it starts at 800 Kelvin at 2 megapascal. That's where it starts, state 1. But now it's not going to go down to almost 350. It's going to go to 400 Kelvin and 0.1. There's exit state 2. Does that seem plausible that you could have it go like that? Sure, because it's going to not violate the second law. S2 is greater than S1 due to irreversibilities. But because of the higher temperature, the exit enthalpy at state 2 goes up. The exit enthalpy at state 2 now is 400.98 kilojoules per kilogram. Hence, the actual work out of the turbine is only 421 kilojoules per kilogram. The next part, what's the isentropic efficiency? Well, the efficiency of this gas turbine would be the work turbine actual out compared to the maximum, which would be assuming isentropic expansion, which you calculate to be 421 divided by 471. And the isentropic efficiency of this gas turbine is 89.4%. So if you want the maximum work out of a steam turbine or a gas turbine, both of those turbines are well insulated, negligible changes in kinetic and potential energy, it's isentropic expansion of that steam, isentropic expansion of that gas. Now I need to talk a little bit about compressors, but before we do that, let's summarize for the gas turbine. So you have a turbine, you have the inlet flow 1, exit flow 2. You're trying to convert as much of the work that's in the fluid into shaft work. So the work out is the change in the enthalpy. Again, it's well insulated and neglect changes in kinetic and potential energy. We could put this on a property diagram, temperature entropy. Think about lines of different pressure, and you start at high pressure. This is a high pressure right there. That's a low pressure. And you expand from 1 to 2, and that will be called 2S. It's isentropic expansion. If you actually have a real turbine, there'll be some irreversibilities. It'll still go to the low pressure, but that's state 2 actual. Sometimes I'll put an A there to say, hey, this is 2 actual versus 2S. 2S for isentropic, 2 actual for actual. And I don't think the book does it, so I think I'll try and leave it off for right now. But it's the actual expansion. If you wanted to say, what is the isentropic efficiency of the turbine? The isentropic efficiency is the work that the turbine actually produces divided by the work, the maximum, which would be isentropic work out. True? So it would be something like H1 minus H2 divided by H1 minus H2S. Okay. If you assume constant specific heats, you have C sub P T1 minus T2 divided by C sub P T1 minus T2S. The C sub P's cancel. Constant specific heats helps us look at the difference between this temperature T1 and the temperature T2S. That length of that line is the greatest. Then you have another length of the line from T1 down to T2 actual. And so the ratio of the lengths of those lines visually is the efficiency, the isentropic efficiency. Now let's talk about a gas compressor. And I tried to put this all on one slide. Comes in 1, goes out 2. We could show the work coming out of the compressor, but you're going to have to supply shaft work into the compressor. True? And what's the purpose of a compressor? Talk to me a little bit about the pressure at 2. Isn't that the high pressure? Where over here, pressure 2 was the low pressure. So the compressor boosts the pressure of the gas. Let's go ahead and show it on a temperature entropy diagram. Here is my line of low pressure. Here is my line of high pressure. Where would state 1 possibly be? Maybe right here. Low pressure. We're going to put it through the compressor. The compressor, we're going to make the same assumption that there's no heat transfer, so Q is equal to 0, and negligible changes in kinetic and potential energy. All right. So where would state 2 be on this TS diagram? Straight above, all the way up to there. and that would be isentropic compression. Last quicker question for today. We know that when we have some irreversibilities, that the compressor's still going to take it to the same high pressure. But I don't know where state 2 actual is going to be. I think it may be over here, or I think it may be over there. Where is state 2 actual for a compressor when you have some irreversibilities present? Yeah, the isentropic, we know what we have straight up. Now I have some irreversibilities. Where is state 2 actual? You need more time? All right. Let's write down the second law for this. If I write down the second law for this control volume around the compressor, right? Do I get that the exit entropy is equal to the inlet entropy plus any generation due to irreversibilities? Do I get that? All right. So is the exit entropy always going to be greater than the inlet entropy? You see the logic why it has to be? Irreversibilities will never destroy entropy. It'll only produce more. All right, so B was the right answer. Let's get rid of that. So what happens is now you did a dashed line over to state 2 actual to understand the performance of a compressor. Think about this. Will it come out hotter because of the irreversibilities? Will the temperature at 2 be greater than the temperature at 2 isentropic? Yes. Right. Because of the friction, because of the irreversibilities. So now let's define a compressor, put a C there instead of a T, a compressor isentropic, and I'm kind of confused. Maybe I'll ask one more clicker question. Would it be the compressor work actual compared to the work isentropic, or the work compressor isentropic to the work compressor actual? I can't, it's either this version or that version. Which one is correct to give me an isentropic efficiency for the compressor? Okay, we're now running. I'll give you a little more time. All right, let me do this. What does the first law give us? Its first law says the work that goes into the compressor per unit mass will increase the energy content of the flowing fluid. Hence, the exit enthalpy will be greater than the inlet enthalpy. That's the first law. WC is H2 minus H1. Right? All right. We talked about if I wanted to know the change in the enthalpy, I could approximate with constant specific heat. C sub P, T2 minus T1. True? Then I look and I say, here's T1, here's T2S. This line right here is multiply that temperature difference by the specific heat constant pressure for the air, and I have the work that had to be provided to the compressor. If I say, well, hold it, it's coming out hotter, right? Do I have to supply more work to the compressor to achieve the same boost in pressure because of irreversibilities? You apply more work and it goes out higher temperature. So, efficiencies. I know that the coach says, all right, let's go out, win this game. Let's go. Give it 110%. Can anybody give it 110%? No, it sounds good in the movies, sounds good in the football coach's locker room and all that stuff. But the engineers, the efficiency by definition is less than or equal to 100%. Maximum efficiency is 100%. I will ask the last question. We have enough time. The same question now. Should it be A or should it be B? Which one is the most logical definition for the compressor isentropic efficiency? All right, I gotta grade them and let you go, but the length of the line is longer for T1 to T2 actual. Hence, you better put that one down in the denominator if you want anything less than 100% or maximum 100%. So it's B. So 75% did well. I wonder what it was before. 56%. So thank you very much.